prove that z inverse of z square plus z by z minus 1 into z square plus 1, which is equal to 1 minus cos n pi by 2. Let capital F of z is equal to z square plus z by z minus 1 into z square plus 1. That is, taking z outside in the numerator, so z into z plus 1 by z minus 1 into z square plus 1. So multiplying both sides by z power n minus 1, f of z into z power n minus 1, which is equal to z power n minus 1 into z plus 1 by z minus 1 into z square plus 1. Now grouping that z numerator z and z power n minus 1. So you will get z power n minus 1 plus 1. So minus 1 plus 1 get cancelled. So you will get z power n into z plus 1 by z minus 1 into z square plus 1. Now to find the poles of f of z into z power n minus 1. For that, take the denominator and equate the denominator function to 0, right? So the poles of f of z into z power n minus 1 are given by z minus 1 into z square plus 1 equal to 0. Therefore, first term, first factor, z minus 1 equal to 0 means z is equal to 1. A simple pole, order is 1 because z minus 1 power 1, right? Next, z square plus 1 equal to 0. So z square equal to minus 1. So z is equal to root of plus or minus root of minus 1. So you will get z is equal to plus I comma minus I. Power is 1. So simple pole, right? Right. Next, R1, residue. So we know the formula. Residue of f of z power n minus 1 at z is equal to a. That is equal to limit z tends to a, z minus a into f of z power n minus 1. Here, first one, take a is equal to minus 1. So you will get R1, which is equal to limit z tends to 1, z minus 1 into z power n, right, into z plus 1 by z minus 1 into z square plus 1. Here a is equal to 1, right, not minus 1, sorry, right, a is equal to 1. So limit z tends to 1, z minus 1 into z power n into z plus 1 by z minus 1, z square plus 1. So z minus 1 in the numerator and z minus 1 in the denominator get cancelled. So you will get limit z tends to 1, z power n, z plus 1 by z square plus 1. So replacing z by 1, so you will get 1 power n, 1 plus 1 by 1 plus 1. So you will get 2 by 2, that is equal to 1. So residue, first residue is 1. Now we need to find the second residue when z is equal to I, because we are having 3 poles, a is equal to 1, a is equal to I, a is equal to minus I. So we need to find 3 residues, R1, R2, R3. R1 with a is equal to 1, R2 with a is equal to I, R3 with a is equal to minus I. So we will get limit z tends to I, z minus I into z power n, z plus 1 by z plus 1 into z square plus 1. So factorize z square plus 1 in the denominator. You will get limit z tends to I, z minus I into z power n, z plus 1 by z minus 1 into z plus I into z minus I. So numerator z minus I and denominator z minus I get cancelled. So remaining you will get limit z tends to I, z power n into z plus 1 by z minus 1 into z plus I. Replacing z by I, applying the limit. So you will get I power n, I plus 1 by I minus 1 into 2i. So I power n 1 plus I divided by 2i into minus 1 plus I into multiply the conjugate of the denominator with the numerator and denominator again. So you will get minus 1 plus I conjugate complex number, right? Minus 1 minus I. You just replace the sign of the imaginary part, keep the real part as it is, whatever the sign is, right? So minus 1 minus I into minus divided by minus 1 minus I, right? So I power n, so multiplying in the numerator, so 1 into minus 1 minus 1, 1 into minus I into minus 1 minus I into minus I minus I square. The denominator 2I into, using a plus b into a minus b formula. So a square minus b square, a square minus 1 square. I'm talking about the denominator. Minus 1 square, you will get 1 minus I square minus I square. I square is minus 1. Already you are having minus, right? Minus into minus plus. So you will get 1 plus 1. 2I into 1 plus 1 in the denominator. So in the numerator, I power n minus 1, I minus I minus I minus I minus 2I, I square minus 1. You are having minus already there. So minus into minus plus 1. So 1 minus 1 get cancelled. The numerator, you will get I power n minus 2I by 2I into 2. So 2I get cancelled. So you will get R2 is equal to minus 1 by 2 I power n. Next R3. Just replace I by minus I. So you will get R3 directly. R3 is equal to minus 1 by 2. Instead of I, you put minus I. That's all right. Minus I power n. Right? Therefore, by the method of residues, f of n, which is equal to sum of the residues. So R1 plus R2 plus R3. So R1 is equal to 1 minus R2 is equal to I power n by 2 minus R3 is equal to minus I power n by 2. That is equation number 1. We know that I power n, which is equal to, right, complex numbers, cos pi by 2 plus I sin pi by 2 power n, right? I can be written as, right? And because cos pi by 2, I can be splitted into like this, cos pi by 2 plus I sin pi by 2. Because cos pi by 2, 0. Sin pi by 2, 1. 1 into I, you will get I. So I can be written as cos pi by 2 plus I sin pi by 2. I power n means cos pi by 2 plus I sin pi by 2 power n. Using De Moivre's theorem. So cos theta plus I sin theta power n, whole power n means cos n theta plus I sin n theta. That is De Moivre's theorem. Using that, so I power n is equal to cos, here power is n. So n pi by 2 plus I sin n pi by 2. And minus I power n. So replacing I by minus I. So you will get which is equal to cos n pi by 2 minus I sin n pi by 2. Right? So 1 becomes f of n, which is equal to 1 minus I power n by 2 minus I power n by 2. Replacing the values of I power n, you will get 1 minus 1 by 2 cos n pi by 2 plus I sin n pi by 2 minus 1 by 2 into cos n pi by 2 minus I sin n pi by 2. So 1 minus 1 by 2. So grouping all the terms. So 1 by 2 is common. Taking minus 1 by 2 outside, cos n by 2 plus I sin n pi by 2 plus cos n pi by 2 minus I sin n pi by 2. So plus I sin n pi by 2 minus I sin n pi by 2 get cancelled. So you will get 1 minus 1 by 2, 2 cos n pi by 2. 2 and 2 get cancelled. So you will get 1 minus cos n pi by 2, which is to be proved. Thanks.